Hello everyone. So we're at the point where we've done a lot of work with the discrete Fourier transform, and this is a great analysis tool. But I also want to introduce you to another analysis tool called the Z-transform, which can sometimes be more appropriate. So let me first review a couple peculiar things about the discrete Fourier transform that kind of leave us wanting something more. So one of them is, okay, look, the discrete Fourier transform is totally fine if you have a periodic signal that goes through an integer number of cycles over the analysis window. In this example, I have a sinusoid going through 3 cycles over the window, and so I only need to use the index 3 cosine or the index 3 sine. But as you recall, if I don't go through an integer number of cycles over the window, I end up with something called spectral leakage. I actually need all the frequencies to represent my signal because the discrete Fourier transform assumes that this thing repeats itself going through an integer number of cycles over the window. And so that's already a little weird. So the presence of this window kind of forces us to coincide with the analysis frequencies that fit an even or an integer number of samples through the window. Okay. Another thing that's interesting is if you recall the convolution theorem. So if I were to say, let's say a simple low-pass filter here. This is kind of like the simplest low-pass filter. And I were to do the convolution of x and h. We could do that, that's fine. But in order to apply the convolution multiplication duality theorem, what we need to do is actually zero pad h so that it has the same number of samples as x. So what I would say here is actually h pad is equal to np dot zeros like x, and h pad 0 and h equals h. Okay, so I actually need, in order to apply convolution multiplication duality, I actually need both of the signals to be the same length. But once I do that and I plot some things, we'll see the familiar identity. So let me just do that real quick. Okay, so here's where we see the familiar thing. Absolute Fourier magnitude of the original signal is this. Absolute Fourier magnitude of the zero padded impulse response is this. And then absolute magnitude of convolution is this. So you can see the point-by-point multiplication of the original two magnitudes at each frequency ends up being the magnitude of the response here. Now this only makes sense though if the impulse response has as many samples as the original signal. So we had to zero pad the impulse response to have over 60,000 samples, even though the impulse response only had 2 non-zero samples. Okay, so that's a little weird. And I mean, we could do it, it's fine. And actually the more I zero pad it, it'll just lead to more interpolation in the Fourier domain. But this actually won't work at all for other kinds of impulse responses called infinite impulse responses. There's no window that could contain them. So, I mean, if I have an impulse response that's short enough, I can zero pad it. But some impulse responses are infinite. And so that's not going to work. So just something about the fact that a discrete Fourier transform has a window is causing us some problems. And that's what the Z-transform is going to come in to address. Okay, so to do the Z-transform, I think it's helpful to go back to the definition of convolution again. And if you remember, what convolution does is it just takes the original signal and it repeats it at each impulse in the impulse response, scaled according to how strong the impulse is at that moment of time. So mathematically, what that translates into is this equation here. So you see, for each impulse at time j, you repeat the entire signal shifted over by j with an amplitude scale of the impulse response at j. Okay, so that's that. Now if I look at this particular example up here, so if I look at this example of the simple low-pass filter, what I have is h0 equals 1 and h1 equals 1. That's it. Everything else is 0. And so if I actually apply this equation, then what I'll see is, so let me call this the result of the convolution here y of n. I'll just use that as my convention. So if I plug this into the equation, what I see is that y of n is equal to x of n plus x of n minus 1. That's it. So the impulse response is telling me, okay, take the entire signal as it is at the beginning of time, and then start it again with a lag of 1 at time index 1. Another way of saying that is just, hey, each sample is x plus what it was before. Okay. So this is called a difference equation. It's just another way to write out a convolution. And what we can do is say, all right, one of the problems I was having a moment ago was if my x was some kind of periodic thing, but it didn't go through an integer number of periods over some window, then I was stuck. Well, let's just try to define the most general periodic sinusoid that we can. All right. So what I'm going to do here is let xn be a phasor, and that phasor I'll say it'll be just e to the I 2 pi fn. All right. And so we'll say where f is in units of cycles per sample. All right. And so that means that f has to be between 0 and 0.5. Okay, so here's the whole thing. So we know that we can't go through more than a half of a cycle per sample. That's the Nyquist theorem. And so, but every other sinusoid we can represent like that. Okay, cool. So now let me just plug that into the difference equation. So what I'm going to get then is that yn is equal to, let me just copy and paste this here, e to the I 2 pi fn plus e to the I 2 pi f quantity n minus 1, right? Actually, this is going to get a little bit cumbersome. Let me switch the frequency units to be in radians per sample instead of cycles per sample. And so that I'm going to find some variable omega, which is just 2 pi times the frequency in cycles per sample. And so now omega is going to be in the range from 0 to pi. So this is a common way that people define this as well. Okay, so then I use omega instead, and here's my equation, a little bit easier to write. All right, now, but we got something kind of cool going on here with the exponent. I can actually factor this out. I can say I omega n minus I omega, and then split this into the product of two things, because e raised to the a plus b is actually e to the a times e to the b. So I can write this as e to the I omega n times e to the I omega times negative 1. Or I'll just write it as e to the negative I omega. All right, and so that is a very nice thing we could do because of the rule of exponents. And now we notice that these two additive terms have something in common that we can factor out. And so I can actually write this as y of n is equal to e to the I omega n times the quantity 1 plus e to the negative I omega. All right. And so this, what I'm really trying to do here, what this is all about is I would like to find out what happens to the phasor that I put in. I would like y of n to be a phasor that I can look at and compare to the input phasor x of n. Now, if you remember, the canonical form for phasors is some amplitude, which is a real number, times a pure phasor, a magnitude 1 phasor. And I'm not quite in that form yet. I have a magnitude 1 phasor here, but I've got a mix of a real number and some magnitude 1 phasor here. So what I have to do actually is multiply by a fancy 1. And so here's what I'm going to do. I'm going to multiply this by e to the I omega over 2 over e to the I omega over 2. And hopefully you can agree with me that this is going to be 1. Because actually this can never be 0. For any omega, this is going to be non-zero. So this will be 1. Just the 1. But why would I do that? Well, now I can actually distribute the numerator of this through here and the denominator of this through. And I end up with this expression. Now, it looks like I made it worse. Okay, so what I did was I took the denominator, I rewrote it over here. This is e to the negative I omega over 2. And then I distributed the numerator through here. So it looks like I made it worse. But actually, I can use a trig identity here, which is that e to the ix, so e to the ix plus e to the negative ix is equal to 2 times cosine of x. And that's actually just going back to Euler's formula. So if you remember Euler's formula, e to the I x is equal to cosine of x plus I sine of x. So what this is going to do is that'll be cosine of x plus cosine of x plus I sine of x minus I sine of x. So the sine of x term cancels out. And so we're actually left with the real number, which is what I was looking for. So I can rewrite this. It looks like I made it worse at first, but actually this ends up just being 2 cosine of omega over 2. All right, and so now I'm at the stage where I can really, I've got a nice expression, because when I look at this, let me put one more pair of parentheses here. I can actually see now the original sinusoid, e to the I omega n. And I can see the output is what the input was, but times this phasor. Okay, and when I look at this phasor, I see it has a slight phase shift of e to the negative I omega over 2. And it affects the amplitudes by this. Okay, so the real part tells me what's going to happen, how the amplitude is going to change. This is just a phase shift. So let me actually plot this. I'll say, as I said, omega is supposed to be between 0 and pi. So if I say omega is equal to np dot length space 0 pi, let's look at maybe 100 samples of this. And let me just plot the magnitude part. So 2 cosine. So I'll say magnitude is equal to 2 cosine of omega over 2. And let me plot that versus omega. So I'll say PLT to x label omega, and then PLT.ly label is magnitude. Okay, so here's what we get. Now this should look awfully familiar. If I scroll up, that's exactly what I had here. And that is not a coincidence. But now what we've managed to do is come up with an expression to describe how this impulse response will affect any sinusoid, not necessarily the ones that correspond to analysis frequencies in our discrete Fourier transform. So this is a general expression. I can plug in any omega between 0 and pi here. And those are all possible frequencies that I could represent at whatever sample rate that I'm. And it's probably helpful to go through a little example of this to make sure it makes sense where the theory applies. So let's say I had a radian frequency of, let's say, 1.5. Okay, so 1.5 radians per sample. Let's take 100 samples. So I'll say NP range 100, and let me make a pure cosine at that frequency. So just omega times n. All right. And now if I send, actually I'll call it x. Now if I send that through and convolve that with my impulse response, which is just 1, 1, let me plot that. And here's what I get. Now, so I see it actually is the same frequency. Let me plot x originally. Okay, so x is the blue one, and the orange one is the result of filtering. So I can see it's the same frequency, but the amplitude has changed. So if I go back and look at the equation, I see the amplitude is supposed to be 2 times cosine of omega over 2. So let me write that down here. I'll say amplitude is equal to 2 times cosine of omega over 2. And let me just plot, I'll just plot y for now. And let me plot, I'll say 0 times AA. And I'll plot the negative of that down there. So I want to show you that this is actually between these two. Yep, okay, so this is the equation told me that the amplitude was supposed to be this, and I can see there it is. Let's try, maybe 0.5 instead. Okay, so this told me the amplitude was going to be about, 1.9 or something. And there it is. Okay. Just one more example. Let's choose 2.5. Let's say that. So I'll say omega is equal to 2.5. Whoop. 2.5. And yeah, aside from these, there's some boundary effects here. But once we get rolling, we can see that the amplitude is totally within that range. All right, so cool. So the Z transform is telling us something about any sinusoid. There was no notion of a window here. I just chose some frequency, and I could see the response. All right, but this was just a motivating example, and I'd like to get a general idea for what's happening here. So we saw before that when we looked at h of 0, that just gave rise to the original phasor, right? Then we looked at the phasor delayed by 1, and that was like e to the I omega times the quantity n minus 1. And so if we go back to the general definition of convolution, let's say we have some arbitrary impulse response here, what we can say is that, in general, y of n is going to be, I'll say h of 0 times e to the I omega n plus h of 1 times e to the I omega n minus 1 plus h of 2 times e to the I omega n minus 2, and so on and so forth. So there's a pattern here. And if we do that thing where we factor out the common term of e to the I omega, I can write this. So if I factor out just the original phasor, I can write this as y of n is equal to the original phasor times h of 0 plus h of 1 e to the negative I omega plus h of 2 e to the negative I 2 omega, and so on and so forth. So what we see is when we convolve any phasor with an impulse response, we always get back that same phasor times a very fancy complex number. This is just a complex number. And any complex number can be written as a real number, amplitude, times a unit phasor. The real number amplitude would be what is the scale that I incur. So up here it was like, okay, I put this thing through and it got scaled by 0.7 or something like that. And then there's also a phase shift that's associated with the unit phasor part of it. So let me actually, this is not the way you would normally write it mathematically. I would actually usually write it using sigma notation. So let me do that. So I'll say sum from, I'll say maybe k equals 0 up to, let's say that there's L samples in the impulse response. So this would be h of k times e to the I, or negative I omega raised to the k power. So I'm just gonna write this slightly differently algebraically, but an equivalent expression. So here is the same expression. Let me get my parentheses looking nice here. All right, so same expression. And just to check, when k is 0, this is just going to be h of 0 times some number to the 0 power, which is 1. So it's just h of 0 plus h of 1, that's e to the negative I omega, plus h of 2, my rules of exponents, that's e to the negative I 2 omega, etc., etc. And actually, in general, people write this in an even more general form, where you would say, maybe it's not e to the I omega that I'm looking at in this part. It might actually be just some general complex number called z. Okay. Now we're going to start off making our complex number be this unit complex number e to the I omega. But that's a special case. Z equals e to the I omega. And actually, sorry, I meant to write here z to the negative k. Okay, there we go. Now this all matches. Okay, so this expression in parentheses here is known as the z transform of h. We're keeping our z here as this unit phasor corresponding to the frequency that we're evaluating this at. But this, again, could be a general complex number. Okay, so let me write some code to evaluate the z transform in general for any impulse response. So I'll say get my z transform. And I'll just define it right from the definition here. So I'll say, okay, I'm trying to compute some complex number based on this expression. Let me loop through all the elements in the impulse response. And what I'll do is I'll accumulate, I'll say ret plus equals h of n times z raised to the negative n. And then I'll return that. Okay, so maybe just to check this example that I had up here, So I had this impulse response h, and let me just check, it should still be in memory. Yep, it's 1, 1. So if I were to do my z transform of yeah, I'll just say 1, 1 here. And let me send in the phasor. So e to the I, and then omega here was 2.5. Okay, here's what I get. And actually, let me look at the, so it's a complex number, as I said. I can look at the magnitude of it, right, the real number associated. Okay, and that's 0.63. And, okay, yeah, that's what that number is. Okay, so that seems to work. Let me go one step further here, and I'll just make a little helper method. I'll call it get z over, pi or something. So what I'll do here is, and I'll ask for the number of samples. Let me look at a bunch of z's. I'm going to do the z transform over a semicircle in the complex plane, is what it is. But I'm just going to look over a bunch of frequencies. Is kind of what I was doing up here, right? I was going from 0 to pi. So I'll just make a method to do this in general. So I'll say, okay, my return is equal to np.zeros and samples, p type equals complex. So I'll say, okay, for I in range, or I guess I'll say for omega in np.linspace 0, pi, and samples. Let me, and actually I should say for I omega in enumerate. So let me just, again, take my samples on the semicircle from 0 to pi. I'll say, okay, ret at index I is equal to z transform of omega, and put an exp, or sorry, z transform of my impulse response h with 1j times omega. All right, so I mean, it's gotten a little more abstract with all this, but it's really the same exact thing I already did. I've just generalized it a little bit. So maybe I'll call this, yeah, over pi semicircle. I don't know. I'm having a hard time with this method. Unit semicircle. Okay. So let's just look at this one more time. So I'll say, my ret, or I'll say, z transform equals get z over unit semicircle of this impulse response, and I'll say, 100 samples. And so I'll plot. And actually, let me go ahead and I'll also return my omegas as to go along with this to make this a little bit easier to plot. So I'll say here, omega z transform is get z over unit semicircle. Okay, so let's plot it. And again, I'm just going to look. I know this does a phase shift also, but let me just look at the magnitude first. Okay, so I get the same thing. Whoop-de-doo. Okay, but where this gets more interesting is if we want to do it a more complicated example. So let's say that maybe I had a little ramp that was going down. So I'll say ramp is equal to np.linspace. Let's say it starts at 1 and then it goes down to 0, and maybe it does that over 10 samples. So what does the z transform of that look like? Okay, there it is. So this is also a kind of low-pass filter, but it looks a little sharper, right? So it cuts off frequencies a little higher there. So that's what this impulse response would do. I'll just plot the impulse response by itself real quick. So a little more complicated. We definitely wouldn't want to do that one by hand. It would be kind of a pain. We could, but I don't want to do it right now. There's some tricks you would use. But anyway, so this is the general z transform that we're going to continue to study. But I actually want to do one more example analytically in this video. That's kind of similar to this one up here. But instead of a low-pass filter, it's going to be a high-pass filter. So I do actually want to do one more example analytically. And in the next couple of videos, I'll do more examples analytically. But again, you can always run this code and just do it numerically and see what the z transform would be, and evaluate it at any place on the complex plane, actually. But yeah, let's just look at the high-pass filter real quick, and then we'll call it a day. So a simple high-pass filter would be if instead of I had h0 be 1, and instead of having h1 be 1, I'll have h1 be -1. Okay, so just one little change here. And so the difference is going to be, actually let me jump ahead a little bit. The difference is going to be that instead of 1 plus e to the negative I omega, we're going to end up with 1 minus e to the negative I omega. But I'm going to do the same trick, actually, where I multiply by a fancy 1. And so if I go grab that here, what we end up with is that... Oh, sorry, let me just get this all here. So again, I'm going to change that plus to a negative here. And so now we're in kind of a similar place to where we were before, except this is going to be, instead of 2 cosine of theta, this is going to be 2 times I sine of theta. Because, well, similar reasons. You can use Euler's identity again. And so I'll factor out the I. But yeah, this is going to be 2 sine omega over 2. And I'll factor out the I here. So in fact, the I is actually just, would be a pi if I brought it up. Or it would be a pi over 2 if I brought it up here. But yeah, I'll just leave that there. That's fine. Okay. But magnitude-wise, so yes, there's a phase shift. But magnitude-wise, what I'm seeing here is that this is what it looks like. And if I were to plot it, let's verify this. This should be a high-pass filter. And there it is. Okay, so this only lets the high frequencies through instead of the low frequencies. And some intuition for this would be, well, if I look at the difference equation, then it's y of n is equal to x of n minus x of n minus 1. This is actually a little bit like a derivative. And if we take the derivative, so this is kind of like a very cheap approximation of a derivative. Like this would be like a secant approximation on the left side of sample n. If we suppose that you know, let's just say, I'll do a continuous, I'll wave my hands a little bit and do a continuous example. Let's just say, suppose y of t is equal to, let's say, sine of 2 pi f t. Or maybe I'll just say again omega t. I'll keep it as omega. All right. Then the derivative of this is going to be omega cosine omega t. And so what you see here is that, whoops, sorry, why am I confusing omega cosine omega t? What you see here is that when I'm taking the derivative, the amplitude of the sinusoid goes up the higher I am in frequency. So this is just a little bit of hand-wavy intuition why the derivative would be a high-pass filter. It does more. It has a higher amplitude response for higher frequencies. But this is a cheap derivative. It's not exactly a derivative. Instead of going up linearly like the true derivative would do, it goes up as a sine. But a sine is a good approximation of a line for small angles. So yeah, anyway, that's what the derivative does. Okay, cool. But anyway, that was the z transform. There's a lot more we can do with it, and we will. I'm just going to have you do a quick exercise, another analytical derivation of a particular example.